Welcome back to our investigation into trigonometry. We will be talking about inverse trigonometric functions today. So far, we have been given an angle with measurements, and we have evaluated different measurements for the angle, whether we're given a triangle with known side lengths or a specific angle of measure. Well, what if we want to find the inverse of that so that we can find out what the angle is based on those measurements? Let's say we have an angle of elevation from some sort of relationship, like you've got a tree and you're standing far away from the tree and you want to know what the angle is of elevation. You would want to use an inverse to solve for that angle measure. How do we reverse the process? Well, first of all, let's review inverse functions. Inverse functions are where the input and the output are switched, and inverse functions only happen when you have a one-to-one function. What does it mean to be one-to-one? This means that there's only one input for every output. So it doesn't violate the horizontal line test in addition to that vertical line test. Inverse notation has the function f with a little exponent of -1. It doesn't mean that you are writing this as 1 over f. It's just inverse notation. And in an inverse, the input and the output switch places. So the domain becomes the range and the range becomes the domain. Now, the sine function violates the vertical line test because it's cyclical. So in order to find an inverse sine, we restrict that sine function to a specific domain, and then we can find the inverse. If you don't restrict the domain, you cannot find the inverse because it is not one-to-one. We are going to restrict the domain of sine from -π/2 to π/2. And when you restrict that domain, our range is also restricted. Our range is restricted anyway because the values of sine are only from -1 to 1 unless you obviously have an amplitude change. So if we were to do the inverse of sine, then the domain of sine is between -1 and 1, and the range of sine is between -π/2 and π/2. Here is our graph of the inverse of sine, where the point π/2, 1 becomes 1 π/2. And the point -π/2, -1 becomes the point -1, π/2. And the point 0, 0 stays 0, 0. Now, there's a couple of different ways that you can write inverse of sine. You can write it using the -1 exponent like you see here. That represents the inverse of sine. Arc sine is another way to say inverse of sine. When you say y equals the arc sine of x or y equals the inverse sine of x, what you're saying is that the sine of y is equal to the value of x. Because remember, when you're finding the inverse, you swap the input and the output, and then you solve for that y value to find the inverse. There is an inverse button on your calculator. You will have sine, cosine, and tangent inverses, and they are accessed using the second button if you're using a TI-84. We're going to restrict cosine to 0 to pi rather than -π/2 to π/2. And notice again that the values go from -1 to 1 in the original range, and the range and the domain switch in the inverse. Notation again, the arc cosine of x is equal to y, or the cosine inverse of x is equal to y, is just saying that the cosine of y is going to be equal to x. Looking at the inverse of tangent now, remember that tangent has asymptotes at -π/2 to π/2. And those are vertical asymptotes. So when the domain has asymptotes,
The range of the inverse has asymptotes.
so those π/2 and -π/2 vertical lines become horizontal lines at -π/2 and π/2. And tangent goes through the origin, and the values again switch. And in this case, when I'm restricting that domain, I am not doing an inequality that is equal to, because tangent cannot equal -π/2 or π/2, as it is undefined at those vertical asymptotes. The range of tangent, remember, was all real numbers, and so it went from -∞ to +∞. The arctangent of x equals y, or the inverse tangent of x equals y, just means that the tangent of y equals x. And so again, remember for the inverse, the domains and the ranges switch. What about if we wanted to compose functions? The composition of functions, if you remember from properties of inverse, you have a function f of x and its inverse, f inverse of x. If you compose the two, you get back out the input. So f of f inverse of x is just equal to x, the input. And f inverse of f of x is equal to just x. Well, the same thing is true for sine and cosine and tangent, but we do have some restrictions in terms of the x values. So for the sine of the inverse sine, that's equal to x on the domain from -1 to 1, but the inverse of sine is equal to x from -pi/2 to pi/2. The cosine of the inverse of cosine is equal to x from -1 to 1 again, but the inverse cosine of cosine of x is equal to x on the interval from 0 to pi. Notice that this was the range of the original function and is the domain of the new function, and this is the restricted domain here. The tangent of the inverse of tangent of x is equal to x for all real numbers. The inverse tangent of the tangent of x is equal to x on the interval from -pi/2 to pi/2. So again, this was our range, which then becomes our domain, and this is our restricted domain. We do have three other trigonometric functions. We have those inverse functions, the inverse of sine, the inverse of cosine, and the inverse of tangent. When we are graphing the inverse of these, we are restricting. Look at the graph of y equals secant x. Now, there are asymptotes at pi/2 and -pi/2, which means those vertical asymptotes become horizontal asymptotes.
For the inverse.
And at the point 0, 1, that becomes the point 1, 0. So we can use that to graph the inverse function, y equals the inverse secant of x. So looking at this graph of the inverse, we see that there are horizontal asymptotes at y equals pi/2, and we're going from 0 up to pi. And so our domain goes from 0 to pi, but we have a break at pi/2. So the range is going to be y is between 0 and pi/2, or pi/2 to pi. Y can equal 0 and y can equal pi, but it cannot equal pi/2. So here's how we write our range. The domain is going on forever to the left and forever to the right. So I'm getting smaller and smaller without bound, or larger and larger without bound, except x cannot be between -1 and 1. I can be -1 and I can be 1, but I can't be between those. And so x has to be less than or equal to -1, or x has to be greater than or equal to +1, which you can actually use the absolute value symbol to write that as the absolute value of x has to be greater than or equal to 1. Because when you drop the absolute value, you have the greater than or the less than the negative. So this is the same thing as x is greater than or equal to 1, or x is less than or equal to -1. Let's look at cosecant. The graph of cosecant has asymptotes at pi, -pi, at 0, which means there will be horizontal asymptotes at 0, pi, and -pi. So you can see the asymptote on this graph here. And the graph at pi/2 is 1, which means that at 1 we have a value of pi/2. Same thing for the graph at x equals negative pi over 2 is equal to negative 1. So then we have the point negative 1, negative pi over 2. See that our range is then from 0 up to pi over 2 or from 0 down to negative pi over 2. And I can equal pi over 2 and negative pi over 2, but I cannot equal 0. So y can be from negative pi over 2 inclusive to less than 0, or 0 up to pi over 2 inclusive. And then the domain, again, I can go from negative 1 down to negative infinity, and I can go from 1 to positive infinity. So x has to be greater than or equal to 1, or x has to be less than or equal to negative 1, which again I can abbreviate as the absolute value of x is greater than or equal to 1. Finally, let's look at tangent. Tangent has vertical asymptotes at multiples of pi. So at pi, there's a horizontal asymptote on the inverse. Tangent goes through the point pi over 2, 0, which means we have the point 0 pi over 2
on the inverse. The inverse range then, since tangent has asymptotes at 0 and pi,
is that y can go from 0 to pi, but it cannot include either of those. And then the domain is all real numbers. X can be anything. And that's it for this section.